So we're discussing about the central force motion, and this is the last part of the central force motion lecture series. So in this lecture, as I've said earlier, we are going to find a relation between the orbit radius r and force. Okay. And now more precisely, if I can say, then I would say that we are trying to find a relation between dr by d theta. I mean how r and theta are changing with each other and will relate it to a force. Now why do we want to do this? The reason we want to do this is, if we are given a particular central force, as I said, central force can be weird. It can have dependence like 1 by r cube. It can have dependence like 1 by r4. It can have dependence like 1 by r square, like gravitation that we already solved. So such type of weird central force can be solved, and we can also find how the radial vector depends on theta. So that's our main target. To achieve this, what we'll do is we'll assume a particular potential u of r. So this potential is the potential with respect to the force, the central force f of r. Remember, f of r can be anything. That's why I'm taking a general derivation. Now, can you tell me what will be the Lagrangian? Now we'll derive this entire thing using the Lagrangian method. So in the Lagrangian, you have to do kinetic energy minus potential energy. So what is the total kinetic energy? As we have discussed in our last lecture, the kinetic energy has two parts. One is the kinetic energy due to the existence of radial velocity, and another is the kinetic energy due to the existence of the linear tangential velocity, that is m half m r square theta dot square. Okay, and now there will be a minus of the potential of u of r. So why potential is u of r? Because our force is a function of r, as a result of which potential is also a function of r, because we are dealing with central force motion. Now what if we have a so what if we now use this Lagrangian into Lagrangian equation of motion? Remember Lagrangian equation motion? That was d by dt of del L by del. So what will be the value here? Let us take r. Okay, del r dot minus del L by del r equals 0. Agreed? Now put the Lagrangian into this equation of motion, and you will get an equation which is minus del u of r divided by del r. So this is first part of the equation, and then this side will have m r double dot minus r theta dot square. Okay, so this is the Lagrangian equation of motion. Now you will say that, hey, the Lagrangian equation of motion usually gave us force. I don't see any force here. Yes, there is force. Let me tell you where the force is. Here is the force. You know that negative of the rate of change of potential with distance is actually force. So this equation can be written as the central force is equals to m r double dot minus r theta dot square. Okay, so this is our force related to the central. This is the final equation of motion that we get from Lagrangian, and you know that whatever equation of motion we get from Lagrangian is always a force equation. Agreed? Okay, now we need to do something with our equation. Okay, so that something is, we need to take away the time. So what is this r double dot? This r double dot is d square r by dt square. Okay, so r double dot is d square r by dt square. So we need to remove this time, and somehow I want to bring in d by d theta. So that's my next plan now. This equation of motion has to be converted in such a manner that it contains d by d theta. Okay, so what to do now? So in the next step, just assume a particular variable which is small u, and let this small u is 1 by r. Okay, if the small u is 1 by r, you can easily tell me what du by d theta will be. So du by d theta equals minus 1 by r dr by d theta. Okay, quite easy. Similarly, you can also write this as minus 1 by r multiply d by dt up and down, so you get dr by dt, and again you get a dt by d theta. So what do you get finally? You get so this is r square. Okay, so this is minus 1 by r square. You get r dot by theta dot. Agreed? And you know that time will get anyhow cancelled. If there is a r dot by theta dot, time will get cancelled. Anyways, so what is theta dot? So remember the angular momentum equation. So from the angular momentum equation, theta dot becomes L by mr square. Agreed? So what is du by d theta now? So du by d theta in terms of angular momentum now is minus m by L r dot. Okay, because we have used this here. So now square it. So what will be the value of d square u divided by d theta square from here? Remember, m and angular momentum are constant. So what will happen? You will get minus m divided by L. You get a theta dot and you get a r double dot. Okay, this is quite easy to do. You can do it yourself. Now again, remember what is theta dot is. Again, you can put theta dot as here. You can put the value, and finally what will you get? You will get d square u divided by d theta square equals minus m square divided by L square. So this L is the angular momentum, and there will be a r square and there will be r double dot. Agreed? So now you can calculate, find what r double dot is. So let me do it here. So r double dot is now minus angular momentum square divided by m square. Okay, and then there will be u square, because 1 by r square is u square. Okay, and then there will be a d square u divided by d theta square. Okay, so we have gone from here to here. Agreed? Now use this r double dot into this first equation. So let me take it over. So this one you have to use it in this equation. So if you use it in this equation, then the final, I'm writing the final equation, just solve it yourself. Okay, these are all mathematics, so solve it yourself. Let me do it here. Let me rub this part. Okay, let me do it here. So once you put that value there in the equation, the final form of the equation is this. So I'm just writing the final form. I hope you can do all these things. Okay, so just the final step is you get d square divided by d theta square. So wherever there is a u, just replace it by 1 by r square. Okay, so this is 1 by r plus 1 by r, agreed, equals minus m r square divided by angular momentum square into f of r. Okay, so understand this. This is the final equation that we wanted to derive, because this equation is a relation that we wanted to do here. Somehow we have connected the derivative of r with the force. Somehow we have connected the derivative of r with the force. So now let me give you an example. Okay, so consider I tell you that there is a particular orbit that follows this equation where r is k e to the power a theta. Okay, so this is the equation that a particular orbit is following. Remember, what is this? This is r is a function of theta. And now if I ask you what is the central force who is responsible for this type of orbit, then what to do? All you have to do is put the value of r here and find the value of f of r. Okay, so this is a task for you, and let me write the result. So I hope you do it. So it's just simple step calculations. Okay, these calculations you have to do, because in your exam you should be perfect to do this type of calculation. So I'm writing the solution, and you just take some time and solve this and see if you have got the same answer. So solution is L square divided by mr cube. So what is this? So this is an different type of central force motion where the dependence is on the r cube. Amazing, right? Previously we have studied the dependencies on r square, like the gravitation or Coulombic, but this is a central force that has a dependence on r cube. Now let me tell you something interesting about this central force. This central force actually causes a spiral orbit. This orbit is actually neither elliptical nor circular, but it is a spiral orbit. Okay, so you can understand why things, what to do when you go towards difficult physics or tough problems. So you need some sound theory to understand some amazing things like this. That's why all these derivations are necessary. So I hope you have enjoyed the central force motion. So let me remind you what we have done. In all the previous lectures, we used the energy method and calculated the r as a function of theta using the energy method. And in this lecture, we used the Lagrangian method, and we used the force, and then we related the force with the orbit equation. Quite amazing, right? Previously, we had not done. Previously, in none of the lectures, we have connected force with the orbit equation. And in this lecture, we connected the force with the orbit equation. Okay, and this is the equation that you see in the red box. So this ends your lecture series on advanced classical mechanics. Thank you for listening.